The acceptable impedance range for an equipment grounding conductor at any point, whether it's an outlet, a fixture, or any piece of equipment back to the panel source, should be 1 ohm or less. Maintaining low impedance in the equipment grounding path is absolutely critical for electrical safety. The purpose of the equipment ground is to provide a low impedance path for fault current to return to the source, which then facilitates the rapid operation of overcurrent protective devices like circuit breakers or fuses. When a fault occurs, such as a short circuit from a hot conductor to a metal enclosure, a large amount of current will flow through the grounding conductor. If the impedance of the grounding path is too high, the fault current will be limited, and the overcurrent device may not trip quickly enough, or at all. This can result in a dangerous voltage being present in the metal enclosure, posing a shock hazard to anyone who comes into contact with it. In addition to shock hazards, high impedance in the equipment grounding path can also create a fire hazard. The excessive current flowing through a high impedance path can generate heat, which could ignite nearby combustible materials. Therefore, ensuring a low impedance ground path is essential for both personnel safety and fire prevention. There are several factors that can contribute to high impedance in the equipment grounding path. Firstly, loose connections are a common cause. Over time, connections can corrode or become loose due to vibration or thermal cycling. These loose connections increase the resistance of the grounding path, thereby increasing impedance. Secondly, the improper installation of grounding conductors can also lead to high impedance. For example, using undersized grounding conductors or making improper splices can significantly increase the impedance of the grounding path. Thirdly, corrosion is another factor that can increase impedance. Corrosion can occur at connections within the grounding conductor itself or at the grounding electrode. This corrosion increases the resistance of the grounding path. Fourthly, long grounding conductor runs can also contribute to higher impedance. The longer the grounding conductor, the greater its resistance. Therefore, it's important to keep grounding conductor runs as short as possible. Fifthly, the type of grounding electrode system used can also affect impedance. A poorly installed or inadequate grounding electrode system can have a high impedance to earth, which can increase the overall impedance of the grounding path. To ensure that the equipment grounding path has a low impedance, it is necessary to properly install and maintain the grounding system. Firstly, all connections should be made tightly and securely. Anti-oxidant compounds should be used at connections to prevent corrosion. Secondly, grounding conductors should be sized appropriately for the circuit they are protecting. The size of the grounding conductor is determined by the size of the overcurrent protective device. Refer to the National Electrical Code, also known as the NEC Table 250.122 for proper sizing of equipment grounding conductors. Thirdly, grounding conductors should be installed in a manner that minimizes their length. Avoid long, looping runs of grounding conductors. Fourthly, grounding electrodes should be installed in accordance with the NEC. The number and type of grounding electrodes required will depend on the soil conditions and the size of the electrical system. Fifthly, regular inspections and testing of the grounding system should be performed to ensure that it is functioning properly. Impedance testing can be performed using specialized equipment to verify that the grounding path has a low impedance. There are several methods for measuring the impedance of the equipment grounding conductor. One common method is the fall of potential method. This method involves injecting a test current into the grounding conductor and measuring the voltage drop across a known length of the conductor. The impedance can then be calculated using Ohm's law. Another method is the loop impedance test. This method involves creating a loop that includes the grounding conductor, the source, and a test instrument. The instrument then measures the impedance of the loop. It is important to note that the impedance of the equipment grounding conductor should be measured under load conditions. This is because the impedance of the conductor can change when current is flowing through it. The NEC provides specific requirements for the impedance of the equipment grounding conductor. According to NEC section 250.4, the impedance of the equipment grounding path shall be sufficiently low to limit the voltage to ground and to facilitate the operation of the circuit protective devices in the circuit. The NEC does not specify a maximum impedance value, but it does state that the impedance should be low enough to ensure that the overcurrent device will trip quickly enough to prevent a shock hazard. In general, an impedance of 1 ohm or less is considered to be acceptable. However, the actual impedance required will depend on the specific application. For example, a highly sensitive electronic equipment may require a lower impedance than a less sensitive piece of equipment. It is also important to consider the impedance of the grounding electrode system. The grounding electrode system should have a lower impedance to earth. The NEC requires that the grounding electrode system have an impedance of 25 ohms or less. If the impedance of the grounding electrode system is greater than 25 ohms, an additional grounding electrode must be installed. The equipment grounding conductor plays a crucial role in electrical safety. By providing a low impedance path for fault current to return to the source, it helps to prevent shock hazards and fire hazards. It is essential to properly install and maintain the equipment grounding system to ensure that it is functioning properly. Regular inspections and testing of the grounding system should be performed to verify that it has a low impedance. The equipment grounding conductor, or EG, is a vital component of an electrical system's safety infrastructure. It's designed to provide a low impedance path for fault currents to return to the source, which in turn ensures that overcurrent protection devices, such as circuit breakers or fuses, operate quickly and effectively to clear the faults. This rapid clearing minimizes the risk of electrical shock, fire, and equipment damage. The maximum allowable impedance of an EGC path is a critical consideration. While the NEC doesn't specify a single, universally applicable maximum impedance value, it emphasizes the need for the impedance to be sufficiently low to facilitate the prompt operation of overcurrent devices. A commonly accepted guideline is that the impedance should be 1 ohm or less, but this can vary depending on the specific application and the requirements of the local electrical code. Several factors influence the impedance of the EGC path. These include the length and size of the grounding conductors, the quality of connections, the presence of corrosion, and the overall design of the grounding system. Longer conductor runs increase impedance due to the inherent resistance of the conductor material. Smaller conductors also exhibit higher resistance than larger conductors. Poorly made connections, whether due to loose connections, corrosion, or improper installation techniques, significantly increase impedance. Corrosion, which can occur over time due to environmental factors, adds resistance to the grounding path. The overall design of the grounding system, including the type and placement of grounding electrodes, affects the overall impedance. To minimize the impedance of the EGC path, several best practices should be followed. Firstly, use appropriately sized grounding conductors, as specified in the NEC Table 250.122, based on the size of the circuit's overcurrent protective device. Secondly, ensure all connections are tight, clean, and free of corrosion. Use appropriate antioxidant compounds on connections to prevent corrosion. Thirdly, minimize the length of grounding conductor runs to reduce resistance. Fourthly, use approved grounding methods and hardware, as specified in the NEC. Fifthly, regularly inspect and test the grounding system to verify its integrity and performance. There are several methods for measuring the impedance of the EGC path. A common method is the fall of potential test, which involves injecting a known current into the grounding system and measuring the resulting voltage drop. From these measurements, the impedance can be calculated using Ohm's law. Another method is the loop impedance test, which involves measuring the impedance of the entire fault current loop, including the EGC, the source impedance, and the line conductors. Specialized instruments such as ground impedance testers and loop impedance testers are available for performing these measurements. These instruments typically provide a direct reading of the impedance value. The NEC provides detailed requirements for grounding and bonding in Article 250. This article covers topics such as grounding electrode systems, equipment grounding conductors, bonding jumpers, and methods of grounding. It is essential to consult the NEC for specific requirements related to your application. In addition to the NEC, other standards and guidelines, such as those published by the Institute of Electrical and Electronics Engineers (IEE) and the National Fire Protection Association (NFPA), provide valuable information on grounding and bonding practices. Regular inspection and testing of the grounding system are crucial for maintaining its effectiveness. Inspections should be performed to identify any signs of corrosion, loose connections, or other damage. Testing should be performed to verify that the impedance of the EGC path is within acceptable limits. The frequency of inspections and testing should be determined based on the specific application and the environment in which the electrical system is installed. In harsh environments, more frequent inspections and testing may be necessary. Proper grounding and bonding are essential for electrical safety. By providing a low impedance path for fault currents, the EGC helps to protect people and equipment from electrical hazards. It is crucial to understand the principles of grounding and bonding and to follow best practices for installation, maintenance, and testing. Failing to do so can have serious consequences. In summary, the impedance of the equipment grounding conductor, or EG, at any point back to the panel source should ideally be 1 ohm or less to ensure effective fault current flow and proper operation of overcurrent protective devices. Factors affecting impedance include conductor size and length, connection quality, and corrosion. Regular inspection and testing are essential to maintain a low impedance grounding path for electrical safety.